In the world of digital design, complexity is kind of the enemy. It means more cost, more power, and slower systems. But what if you could take something really complex and, without losing any of its power, make it way smarter and more efficient? Well, that's exactly what we're going to do today, using a really cool technique called state reduction.
Okay, so check this out. On the left, we've got this sprawling 15-state machine. Looks kind of like a tangled web, right? And on the right, you see this sleek, simple 7-state version that does the exact same job. So, the big question is, how in the world do we get from the mess on the left to that clean design on the right? Well, that's the puzzle we're going to solve together, step by step.
And here's our game plan. We'll break it down into 5 simple parts. We'll start with the problem itself. Then we'll learn the 2 simple rules we need to follow. After that, we'll find our first match, see how to repeat the process, and finally, we'll unveil that awesome final 7-state machine. Let's get started.
All right. First up, let's properly introduce our starting player, the original, unminimized, 15-state machine in all its glory.
So this is it. Each one of those numbered circles is a state, which is just a specific mode or condition the system can be in, and the arrows show how it jumps between them. With 15 states, yeah, it's pretty busy. Our mission, should we choose to accept it, is to untangle this thing without breaking any of its functions.
Now, that diagram is great for getting the big picture, but to really get our hands dirty, we need something a little more organized. So we translate that whole diagram into this, a state transition table. It basically just lists out every state and tells you exactly where it's going to go and what it's going to do. This table right here, this is where the real work happens.
So how do we start simplifying? I mean, we can't just start deleting states at random. That would break everything. We need a strict set of rules to figure out which ones are actually redundant, and that is the whole secret behind the row matching method.
And the key idea is this concept of equivalent states. For 2 states to be considered equivalent, meaning we can combine them, they have to pass 2 very strict tests. First, their outputs have to be totally identical. Second, where they go next has to be the exact same. And I mean, both conditions have to be true. It's an all-or-nothing kind of deal.
Okay, we've got our rules. It's time to get to work. The whole process follows this super simple 3-step rhythm. Find a match, rename everything, and then remove the extra. Let's see how it works.
All right, step 1 is to find a match. So we just scan down the table, looking at the rows, and there! Take a look at state 10 and state 12. Let's run our checks. Are their next states the same? Yep, both go to S0. Are their outputs the same? Yep, identical. It's a perfect match.
Okay, on to step 2, rename. Since S10 and S12 are basically acting like twins, we can merge them into one brand new state. Let's just call it S10 prime. Now this next part is super important. We have to go through the entire table and replace every single time we see S10 or S12 with our new name S10 prime. And now for the really satisfying part, remove. Since our new S10 prime state is doing all the work of the old S12, that row is now totally redundant. It's just taking up space. So we can just delete it. And just like that, we're down from 15 states to 14. Easy, right?
So, what's next? We do it again. State reduction is all about repeating the process. We're just going to keep running our find, rename, remove cycle over and over again until there are no more matches left.
So we scan our new, slightly smaller table, and whoa! This time we hit the jackpot. Look at this. States 7, 8, 9, 11, 13, and 14. They all go to state S0, and they all have the exact same output. That is a massive group of 6 states that are all doing the same thing. We can combine all of them.
You know the drill by now. We follow our process and rename them. We'll just pick S7 as the new representative and call the combined state S7 prime. And once again, we have to carefully go through the whole table and replace every instance of those 6 original states.
And now we remove. We get to delete 5, count them, 5 redundant rows. And look at that. With that one move, our table is so much smaller and easier to read. We are making some serious progress here.
Are we done yet? Not quite. Let's scan the table again. It's time to repeat. Now this is a perfect example of why we have to keep repeating the process. Because we just cleaned things up, a new pair of equivalent states has just appeared. Check out S3 and S6. Now that we've renamed a bunch of states to S7 prime, the next state columns for S3 and S6 are suddenly identical. Their outputs already matched, so bingo, we've got a new match.
And at this point, you're a pro. We rename them both to S3 prime, update the rest of the table, and then get rid of that extra row for S6. Done and done.
Okay, let's give our table one last scan. And there it is, one final pair, states S4 and S5. Same story, because we've been simplifying everything else, these two now match perfectly. This is our last pair.
So after that final find, rename, and remove, the job is officially done. There are no more equivalent states to be found. Let's take a look at the final result of all our hard work.
And here it is. After we renamed S4 and S5 and deleted that last duplicate row, this is what we're left with. Go ahead and scan it. You won't find any more matches. This is our fully minimized, fully optimized state table.
So let's just think about that journey for a second. We started with a machine that had 15 different states, and by following this simple, methodical process, we've boiled it all the way down to just 7.
And when we take our final super clean table and turn it back into a diagram, this is what we get. It's clear, it's efficient, and most importantly, it performs the exact same function as that complicated web we started with, but with less than half the complexity.
This side-by-side really tells the whole story, doesn't it? On the left is where we started, and on the right is where we ended up. The same exact function, but with way less complexity. This whole process is so critical in digital design because it lets us build things that are smaller, faster, and more power efficient. So the next time you see a really complex system, it's worth asking, how much hidden simplicity is just waiting to be uncovered?
Thanks for watching. See you next time.